Hello and welcome to another Reigate Maths video. My name is Simon, and in this video we are looking at the probability section of the Year 1 statistics from the A-Level Maths syllabus. In this video we are specifically looking at the binomial distribution, which is very linked with the binomial expansion that you may have done already. If you haven't, don't worry. You can look at that link when you address the binomial expansion in the pure side of things later on. So first off, let's have a think. What is a binomial distribution? So what we are talking about is if we are running an experiment where we are interested in the number of successful trials. So what we're doing is we're repeating an experiment a bunch of times, and we are looking for the chance of getting a number of successful trials. Now, this is not specifically binomial. For a distribution, for this to be modeled in using a binomial formula or format, there need to be a specific set of restrictions. Firstly, there must only be two outcomes. So, for example, win or lose. Yes or no. That kind of thing. If you are trying to measure win, lose, or draw, as that, it cannot be binomial distribution. If you want to take into account those three possible outcomes, you'd have to use a different distribution, or instead of thinking of it as win and lose, it might be win and not win, or lose and not lose, where that not takes into account both of the other outcomes. So there must be strictly two outcomes. The next thing is there is a fixed number of trials. And the letter we use to represent that is n. N is the number of trials. What we mean by this is if you do an experiment with, say, 40 trials, and then you want to use that information to make predictions about a different experiment, the experiment you're making predictions about has to have the same number of trials as the first one for it to make sense. Otherwise, your calculations and your probabilities are irrelevant. What is also very important is each trial must be independent. This is very important because it tells us information about the fourth restriction, that every trial must have the same probability of success. So every trial must have the same chance of being successful. And the letter we use for that is P. So if we are, say, rolling a die, and we're looking at getting a 6 or not a 6, if that is our experiment, that is binomial. We have two outcomes. We're going to roll a die a certain number of times, let's say 10. Each trial is independent because every trial has the same probability. 1/6 chance of getting a 6. Now, if we change our experiment to say, okay, I'm going to roll a die. If I get a 6, I then roll twice. That's no longer binomial, because what the success of one trial affects the next one. The trials are not independent. So that's what we're saying there. Every trial, the success or failure of one trial cannot be affected by another. Now, the notation for this particular type of distribution is a little strange, but it's very common when you start talking about specific distributions. So we have our discrete random variable, x, and then we use this symbol here. This is a tilde. And then we say what type of distribution it is. Just use a letter. In this case, it's binomial. And then we list the parameters of our distribution. So the parameters, so let's just go through this. So we have our discrete random variable, x. This kind of reads as is distributed. And then the letter here is the type of distribution. So B for binomial is the one you look at in the first year. In the second year, you look at what's called the normal distribution. And if you start doing some of the more advanced statistics in the further maths, you may well look at the Poisson distribution. Depending on what distribution you use, you change the letter. This information here are known as the parameters of the distribution. It's the things that we know about the distribution, the things that we can measure. So for binomial, the things that we set are the number of trials and the probability of success. Those we set, so those are our parameters. So in this case, n is the number of trials, p is the probability of success. For different distributions, you'll have different parameters because you measure or know different information. So what we're going to look at now is some further information about this distribution. Now, in terms of calculation, this is a little more tricky than the previous video for discrete random distributions, where we could draw a table and work out some probabilities by looking at our table. We can do that here, but the probability of getting a number of trials or a number of successes is given by a specific formula. So the probability of getting a certain number of successes. So that's what we're saying here. This is the probability of R number of successes. So R could be 6, it could be 5, it could be 17, whatever. This is given by the following formula. N choose R, P to the R, 1 minus P to the N minus R. So let's just break down this formula. P is the probability of success, R is the number of successes. 1 minus P is the probability of failure, N minus R is the number of failures. But what's this all about? You may have seen it written like this before, but what is it really? Let's look at a sort of thought experiment to see what this is and where it comes from. So this is the example we're going to look at. We are rolling a die 5 times. X is the event we get a 6. Find the probability that 3 6s are rolled. So first off, this is definitely binomial. We have a fixed number of trials. It's a fair die. I didn't write that down, but we'll say it's a fair die. So the probability of success is the same. We're not having any effect. We're rolling one die doesn't affect another. So the trials are independent, which means the probability of success is the same. So we know that this is definitely binomial. We have 5 trials and probability of success is a 6. So remember, this is N and this is P. We want the probability of 3 successes. Now, what people tend to do with this to start off with is go, okay, well, I know how probability works. So it's going to be the probability of getting a 3 once, times again, times again. So the probability of getting a 3 once probability of getting a 3 a second time, probability of getting a 3 a third time. Probability of not getting a 3 and not getting a 3, which is fine. This is not true. Because what are we considering here? We are considering the possible outcome of getting 3 6s first and then 2 not 6s. This is different to that outcome of getting 2 6s, then not, then another 6, then not. The probability of both of these outcomes is the same, because we've got a sixth times a sixth times 5 over 6 times a sixth times 5 over 6. It's the same numbers all times together, they're just in a different order. These are equal to the same thing, which again is then going to be the same as this one, for instance, and so on. So the probability that x is 3 is not just this. It's all of these added together. So this n choose r business that's on the front is the number of ways that this orientation can happen. Now, with a small number of trials, or a small number of trials, you can write them all out. But if you've got 10 or 100 trials, that's not feasible. There is a formula for it, which is a bit of a mess. You are given it. But you can also find it on your calculator. So we know that the probability that x equals 3 using this formula is 5 choose 3 times the probability of success to the power of the number of successes times by the probability of failure to the power of the number of failures. This we can just all stick in our calculator. The alternate notation for this is that. And you'll see this notation when you do the binomial expansion in the pure. The C stands for combinations. It's the number of combinations of these 5 letters, or these 3 and 2 letters. This is not on your calculator, this is. They are the same thing, but that's why I like to write it like this. So, if you get your calculators, if you look at the divide button, you'll notice above it you have NCR. That's this here. So 5C3. And that will give you this number. We can see there's 10. So what this means is there's 10 different ways of writing 3 Ys and 2 Ns. That's what that means. Now, in reality, you don't have to write this out every time. You can just, this is good enough. This shows use of the formula. So this, you can just type in your calculator. So, being careful with typing in your calculator. So we've got 1 over 6 to the power of 3 times 5 over 6. Oops. To the power of 2. Now we could write it as a fraction, but typically we'll give our answer to 3 significant figures. So in this case, 0.0322. So there's about a 3% chance if you roll 5 fair dice, there is a 3% chance of getting 3 6s. Which is not big, but that should be expected. The thing with this is, you only do this if the question says, use the formula. Okay, you only do this if the question says using the formula or words to that effect. So let's just look at an example where that happens. So this is the example we're going to look at first. It is given that in a particular school 30% of the students take English. A sample of 7 students is taken. Now we should specifically say a random sample. Use the formula to calculate the probability that A, exactly 2 students take English, or B, at least 1 student takes English. So if you pause the video now, have a go at this question yourself, then come back and we'll go through it. Now the first thing we should do, or we have to do with these questions, which is typically something that students miss in terms of the full answer, is explaining our variable. So X is the event a student studies English. And then we need to write out our distribution. So we know X is binomial. The number of trials is 7, because that is the sample size we have. And we know the probability of success is 0.3. So for part A, we are looking to find probability that X equals 2. So there are 2 successes. So using the formula, we have 7 choose 2 times P squared, so the probability of success to the power of the number of successes, times 1 minus P to the number of failures. Stick this in your calculator and you get the answer. So we've got 7 C2 times 0.3 squared times 0.7 to the 5. Now, see how my calculator's come up with math error. This is important. The reason being is because of the way I've typed it in here. When you type things in your calculator, if you don't put a times sign, what the calculator is doing is 2 times this, then 7 choose the answer, which doesn't work. In order to get around that, we need to put a multiplication sign in there. And now it gives us the right answer. So that's what I mean by be careful with how you type things in. So we can see here that the probability of having exactly 2 students taking English is about 31%, 31.8%, so 0.318. We write it as a decimal, we don't write it as percentages unless you're asked to. So, we are now trying to find the probability that at least 1 student takes English. Now the formula is specific for equal. It can't cope with inequalities, but this is okay. If we think about the possible outcomes, so if we were to write this as a table, our top row would be, okay, no students take English, or out of 7 we can have this many number of students. In our sample of 7, we could have none that take English, we could have 1, and so on. What we want is this whole section here. Now this is what we want. If we add this bit here, this has to add up to 1. This little section is x equals 0. So this probability is 1 minus the probability that x equals 0. Now, we can use the formula here, but it's a little unnecessary, and I'll explain why in a sec. The reason the formula is unnecessary is here, 7C0, anything C0 is 1, and anything to the power of 0 is 1. So these are generally irrelevant. So we're actually doing 1 minus 0.7 to the 7. Which if we do on our calculators again, we get 0.918. So about a 91% chance that in our sample, at least one student takes English. This is using the formula. Again, only do this if you are told to. Otherwise, your calculator will do this for you. So here is another example. In a period of 6 days, the probability of it raining on any day is 0.2. Find the probability it rains on exactly half the days and at least one day. So again, let's write out what x means and then write out the distribution. So x is the event it rains on at one day. And x is the event it rains. Just keep it simple. So we know x is distributed binomially with 6 trials and probability of success 0.2. So we are finding the probability that x is exactly 3 because half of the days, p is 3. Now we could use the formula, but what we're going to do is we're going to use our calculator functions, which is why it's important that you have this calculator for the exam. So, to go through how you do this on the calculator, you press menu and then go down to this sort of bell curve shape. You can either do that using the cursor or you can just press 7. Now, here we're going to have a lot of options. These first 3 you'll use in the second year. The one we're interested for this example is this binomial PD. The reason we choose this one is the fact that it's equal to. Okay, we'll look at what happens with the other ones in another video. So we choose binomial PD. We choose variable. If we choose list, what you'll do is you'll type in a bunch of x values and get the probability for each. We're only interested in this one. So here, x is the number of successes. N is the number of trials. And P is 0.2. Type it all in, press equals, and it gives you the answer. And again, give it to 3 significant figures. And that's it. You don't have to do anything else. This is not going to be a large number of marks. Now again, part B. Like the previous example, we're doing x is greater than or equal to 1. Which, like the previous example, is probability of that. So let's use our calculator again. Now we've already got all this information stored. So if we press equals, it just goes back to this. We're keeping the distribution the same and just changing the x value. Now for this, because we are using this, I tend to write down the whole thing. Now the other good thing about these calculators is this is now stored as the answer button. So if we go menu and then back to 1 for our normal calculation, if we just type in 1 minus answer, the calculator does it for us and we can then round it. Now for this question, you may get a question saying, as a part C, why might the binomial distribution not be a good model in this case? The way you answer these questions is you think about those 4 things that make the binomial A distribution. So remember, those 4 things are: we only have 2 outcomes, we've got a fixed number of trials, each trial is independent, and each trial has the same probability of success. And you've got to think about, for this situation, which one doesn't work, or which ones don't work. In this case, it's raining. If it rains on one day, it's more likely to rain on the next, potentially. So the trials are not necessarily independent, so binomial might not be a good model. Something like that. That's it for binomial PD. So when we're finding exact values, what we'll do in the next video is look at cumulative distributions when we do inequalities like this. Thank you for watching.